mechanical engineering at first. Recently, I was the mechanical engineering manager at Robotics. I'm a FIRST alumni. I was on an FRC team for 4 years in high school. I've mentored both FTC and FRC since then. Most recently, I was the design mentor for FRC team 3005 in Texas. And I also mentored their family of FTC teams as well. This presentation is kind of a project documentation for something that myself and the rest of the members of 3005 worked on for the 2024-2025 FTC and FRC seasons. I clickbaited you a little bit. It's not necessarily a pitch for you guys to CAD your wires. It's kind of an overview of what we did and how it might be beneficial for your teams. This project is a little bit rough around the edges still, and it still needs some more work. But I'm hoping that maybe some people are interested and want to kind of join in or test drive it on their teams and kind of help add to the project in the future. Because I just moved here to New England recently, I won't be with 3005 next season, so there's not going to be a lot of continuity on this project on the same team. So, you know, that kind of complicates things a little bit. But we've got a quick overview of what we're going to cover today. So we're going to kind of talk about the state of the art in terms of what putting electrical devices and wires and cables in a CAD model looks like currently for FRC teams, kind of the current state of electrical wiring in FRC and FTC in general, and also how that is used in industry outside of FIRST. Then we're going to do a quick overview of what we did for this most recent season on 3005, talk about what the motivation and benefits of that were, and then we'll go into a little bit more detail about what we did. We'll talk about some kind of next steps that I have planned for the project, and then we'll have time for questions at the end. So first, we're going to talk about kind of the state of the art in terms of like the relationship between CAD and electrical for FTC and FRC. One of the big issues that a lot of teams faced, and 3005 was no different, is trying to get your robots to be reliable electrically, right? A lot of times when you are watching matches and the robot's not moving or not acting correctly, you know, or your robot's not performing the way you want it to on the field, usually it's something electrical. Like mechanical failures are not quite as common as electrical failures are. You've got a lot of impacts. You know, we're very space and weight constrained on our robots. A lot of the connectors that we're using are, you know, maybe cost optimized because, you know, we're an educational program and we're not using aerospace grade hardware, right? So it's like not everything is rated or intended for like 50G impacts, which FRC robots can see. And, you know, with a lot of the like high bandwidth, high speed communication pathways that we've got, especially like CAN, you know, those are just very sensitive to even very small connection problems in your cables, right? There's a lot of really common issues that teams see in their wiring that might cause failures of their robot. You know, that might be some issue that exists that you would be able to catch if you could see or get to the electronic devices or the wires, but because the robots are compact and you're very space constrained, you don't have good visibility, you can't maintain it in the pit, and so that can kind of allow issues that could be fixed to go out to the field and cause, you know, matches to go poorly. In addition to that, you know, again, space constrained, you may have interference or, you know, pinching or pulling of wires because of moving parts that are, you know, getting in the way of that. And then, you know, poor constraint of cables, right? Like not a good place to cable tie something down, not a good place to kind of constrain the wire, or, you know, you're over constraining it and things are getting pulled or stressed connections or things like that. So we're going to kind of talk about trying to address some of those issues by better planning for your wiring in your robots, and that's kind of what the intention of this project was. So basically putting actual wires and actual cables in CAD in a FIRST robot is very rare, right? There are a few teams that do it, but maybe not very consistently, maybe not the whole electrical system. It's a little bit more common for like off-season projects or like CAD-a-thon robots where you like really want that pretty render, but it's not a particularly functional thing that a lot of teams do. It's just CAD practice for most of the projects that do it. And that's just because it takes a really long time. And when you are trying to gain every advantage you can over your opponent, you've got to use your time really well. Like the cost-benefit ratio is the most important thing for spending hours in CAD. Beyond that, even just positioning your electronic devices in CAD, like you've got a belly pan and putting the RoboRio and the power distribution and finding a place for the breaker, even that is like a relatively difficult thing to do right now. And a lot of teams just skip it, right? They'll just be like, I've got a big belly pan at the bottom of my robot, I'm just gonna leave it blank, and we'll figure out the placement of everything exactly later, right? That's a very, very common thing to do. And sometimes that's okay if you've got a lot of space available, and then sometimes you get into real trouble later on and you're sad because stuff doesn't fit. And so device mounting is sometimes figured out kind of just on the final robot, and wiring is almost always figured out entirely on the final robot. And that's kind of the way most teams do it. 3005 is no different. Kind of a little bit more detail of 3005's process kind of before we took on this project, specific to FRC. We build 2 robots. The practice robot gets built first. We kind of don't put much of the wiring in CAD, figure it out live on the practice bot once it's mostly assembled. Then we would take what we learned there, kind of pause everything, go back to CAD for usually several days, either revision stuff or make new designs for new panels, add holes, move things around, design 3D printed parts to hold cables in place or whatever. And then basically we would then kick off all of that to move on to the competition robot. Did I lose it? Here we go. FTC is kind of a similar thing, but there's some issues that are made even worse because FTC robots are so small. You're very, very space constrained. The cables and the electronic devices don't really scale down as you scale the robot down, and so they take a very large percentage of the overall robot. So all of the problems that you would see in FRC are even worse in FTC in terms of like trying to make sure things are packaged in this tight space, properly constrained, not getting pinched or pulled as things move around. In addition, 3005 also runs a relatively unique FTC program where we basically have a bunch of teams. We had 10 last year. We basically take the after-school portion of the program, have some of the experienced design students design a very simple FTC robot to play the game in the first few weeks of the FTC build system, and then those designs get kind of mass manufactured, and then all of the other after-school teams and all of the teams in the classrooms build the same robot as a starting point. And when you're having to build this robot to kind of test the first article to make sure it's good, figure out the wiring, and then go back to CAD, it really kind of delays that whole process. And so the classroom teams have to wait to kind of start building their kits until after the wiring is figured out. And so the workflow kind of gets in the way of that. In terms of kind of what is done outside of FIRST in more general industry, most CAD packages have an environment or a set of tools called cable and harness. There's a couple of screenshots from a few different CAD packages. There's kind of a semi-official cable and harness set of features and tools for Onshape as well. It kind of utilizes a whole set of data and libraries that are typically generated either in another portion of the program or a separate application entirely. Maybe you have some ECAD generating a wiring schematic, and it's spitting out a CSV file of a bunch of to and from connection points and everything, connector types, wire types. There's a lot of data, right, that goes into this. That's pretty, pretty involved, and it's typically done after all of the rest of the design is done, right? You've got a pretty complete model in place with the mechanical design and everything in place, and then you're kind of layering this cable and harness set of features on top of that. And it's particularly optimized for things like automotive or aerospace, where they're pre-making a cable or a wiring loom on a pin board in a separate part of the manufacturing process. and then they're kind of taking this full complete wiring assembly and installing it into the final assembly, which is not the way that we build our robots, right? Like that's a relatively time, labor, and kind of overhead intensive way of doing electrical. It's very good in a production environment. It's not so good when you're building 1 or 2 robots. So these features are very much optimized for that workflow, not the workflow that we use in FIRST. Just some reasons why this is done this way and used in industry. Obviously, similar motivations in terms of like figuring out, packaging, space constraints, kind of where things are going to get routed and how to fit everything into tight, volumes. Another big reason is, having a good bill of materials for like cost, estimation, inventory, things like that. If you're working in like aerospace or automotive, like you care about the weight that your wiring loom is adding to your vehicle, and so this helps you get a really accurate model to estimate weight for that stuff, exact lengths for your cables, weights of your connectors, everything. And then in addition to that, you've got this fully CADed thing, so you can build drawings and work instructions and things like that. So in terms of why are we not just using cable and harness like commonly in FIRST right now? It's time is the big one, right? It takes a lot of data coming from those kind of like ECAD side of things. All of that data is a very time-consuming thing to put together and kind of translate into the final wiring CAD model. Also, because of when you're doing this in the process, doing iteration is really time-consuming, right? Because you're kind of like doing most of your mechanical design, and then you're adding the wiring, but then if you discover some problem, you've got to go undo a bunch of work or throw away a bunch of work on the mechanical side, and then come back and tweak the wiring model later. And so that really tight, fast iteration that we have to have, with our robots is not super possible. In addition, the connector libraries are usually kind of a pain point, and this differs software to software and kind of like what you're doing, but most of the time you're making the library of connectors and like cable and wire data yourself. There are some like pre-built ones that get distributed, but they may not have what you need. They're especially, again, optimized for like standard aerospace or like automotive connectors, things like that, and like using kind of the more like low-cost hobby-grade connectors that we're using in FTC or FRC are not generally present in these libraries, and so you have to kind of go develop that stuff yourself, and that's additional setup time and labor that you have to do if you wanted to use a cable and harness environment on your robot. And then in addition to that, like I mentioned, these are meant for building pre-assembled wire looms on a pin board, not cable tying pre-made cables to a like piece of extrusion, right? Which is like the way that we kind of build our robots. And so you're kind of, when you're working in a cable and harness environment, you're kind of fighting against the like natural flow that software workflow wants to have, because we don't wire our robots the way that you would wire a car, right? Okay, so we're gonna kind of briefly talk about what we did to kind of address how do we do a better job planning out wiring on our robots, and make it faster and more suited for what our needs than a cable and harness environment. We're gonna do a quick overview, and then we'll go into a little more detail later. Okay, so this is building on top of a workflow that I call high fidelity block CAD. Now, quick show of hands, who was in this room for the last presentation by Ronan? Okay, most of you, but not everybody. So for those of you who are in this room, this is very related to that presentation. Actually, it's really nice that you guys did that presentation before this, because this is a very related topic. You guys have some background. I don't need to do as much explanation. I did a presentation at the California Mentor Conference last year about high fidelity block CAD. There's a YouTube video of that talk. The slides are public. There's a thread on Chief about it. If you want to go look it up, I recommend checking that out if you're not familiar, because what I'm talking about today is going to be heavily built on that. That is a workflow that we do in Onshape. Basically, from this point forward on the talk, basically only going to talk about Onshape stuff. Technically, the workflow that we did is possible to do in another CAD program, but you would have to do a lot of work to get there, and like there's some custom tooling and features that we've made to enable this that's unique to Onshape. So basically this high fidelity block CAD workflow that 3005 does is kind of building this simplified 3D block model of the final robot, which you see here on the screen. This is not that unique. There's plenty of teams that do this. The 3005 approach is a little bit more involved compared to what like most teams are doing right now. And it's building on top of the existing kind of top-down workflow that Ronan outlined in his presentation, so there's a lot of similarities there. There's a few key differences, and they have some benefits that I won't go into here just for time. But the key differences are we're kind of building our layout sketches, which is what Ronan called master sketches in his presentation. And then we're in that same document, we're building this block model based on those layout sketches. And then instead of referencing layout sketches in our subsystems, we're only referencing the block CAD. And that's like a hard and fast rule. Like, we are never deriving a sketch into a subsystem. We are only referencing the block CAD. Again, there's reasons for that, but I won't go into them there. The critical thing here between the way that we're doing block CAD and the way that like most teams have been doing block CAD for a while now is that we're using final, precise positions and sizes for these block components. So like when we're modeling a plate, right, we're modeling that plate at the actual thickness it's going to be on the final robot, right? And because the whole point is like accurate space claims and referencing your final model on your block CAD for actual positioning relative to themselves. We're figuring out like shaft locations, motor positions, gear center to centers, all that stuff's happening in the block CAD. We have this very accurate 3D model of the robot in this really simplified environment. The key thing here is this is done first. Very early in the design process, we have pretty good space claims for everything on the robot, not a single detailed part with holes and chamfers and stuff in it has been designed, right? We've kind of evolved this process over several years, and so this kind of like this wiring is built on top of that progress. And so the key like thing that we're trying out is like, okay, move the electrical design into the block CAD, right? We're doing most of the decision making in the block CAD process already, so move the electrical into that as well. That allows you to influence the mechanical design of your robot based on the needs of the electrical subsystem, right? Which is the critical thing that's missing in a lot of first teams design and like CAD process right now. So if I need to move structural elements around to make wire pass-throughs possible, I can do that really fast and really easy in the block CAD as opposed to throwing away a bunch of detailed design that I've spent a lot more time on. Also, because you're doing it earlier in the process, there's kind of a psychological element to it where like you're not feeling the crunch of, oh God, competition is in 2 weeks. I need to hurry up and build the robot. I haven't cut parts yet. I need to go, go, go. You're kind of still in this like, I'm gonna do this right, plan it out. You're less likely to skip this process, and that will end up saving you time in the long run, but like you're kind of tricking yourself into doing it when you should. This is still kind of related to a cable and harness workflow, like it's borrowing some concepts and methodologies from it, but it's significantly faster. It cuts out everything that's not necessary, and it's really optimized to try to do iteration quickly and in a really approachable way. Obviously, this is custom stuff that we've developed ourselves, so it's completely optimized for first teams, right? Like I don't know that this would be something you would want to use like in industry, but it's meant for first robot design. And then, like I said, there's some custom feature scripts that we made to do this, and so that's a unique thing to Onshape. All right, so what we did was we kind of started blocking out these features and working on them in the fall. We kind of test drove it with the FTC robot. You can see a couple of images there kind of on the left. A little less components than an FRC robot, and so a little bit easier to test drive. We made iterations and improvements, and then we kind of put it on the FRC robot for real. Okay, so that's kind of a high-level overview. We'll go to more detail in a minute. So let's talk about kind of like what motivated us to do this and what some of the benefits were. So this is related to the kind of higher level block CAD workflow, but it's a lot of it's centered around making sure all the designers are on the same page about what goes where and how much space they have to work with. And so that's similar for electrical, right? Like if you have a subsystem that's sitting in the middle of like a big cable run from one end of the robot to the other, and you've got one student working on that subsystem, but the electrical is not part of their subsystem, you still have this in this block CAD model, and you've kind of claimed that space. It's visible, everybody's on the same page about where all the devices are on the overall robot, what volumes your wires pass through, and there's no confusion about, oh, you didn't leave enough space for the wires that run to my subsystem over here, because that's all physically in the model. There were also a few other things that benefits just kind of popped up. It wasn't specifically planned out, but this block model of the wiring was useful outside of the design phase, right? Like it was not only useful to the CAD students and mentors, it was useful to the build team. When they were wiring the robot, they would kind of just pull the model up, have it up on a screen so they could see where all the connections were. We didn't need to make drawings or anything like that. They could just reference the 3D model, and it's detailed enough that they can just say, yeah, where do these cables run? Okay, I'm gonna cable tie it to this part over here, right? And that kind of just happened passively, right? The students just kind of took that on and just used the model that way, which is a great benefit. Similarly, the programmers would reference to it if we hadn't told them like the ports where something would go, they would just go to the model and look at, oh yeah, this is where this wire plugs into, right? And so they would just set the port number to the correct thing in code ahead of time. In addition to, with our kind of starter bot model that we did for our FTC teams, having this 3D model of like, here's where all the cables go, right? They're using all the pre-made cables, so they just kind of plug in. So it's really easy for the students to kind of just look at this model and be like, okay, I'm gonna take this cable, I'm gonna plug it in here, I'm gonna plug it in here, I'm gonna route it like it shows in the model. And that's really good for a teacher who's in a room full of students and they can't go kind of explain things individually. There's a lot of students compared to one teacher, and so they can kind of do more on their own autonomously using this model. Particularly this workflow is well suited if you have multiple robots. I kind of mentioned how we build the practice robot first, then there's this weird pause where we go make the CAD work for the wiring better, and then we start the comp bot. That kind of goes away or is drastically reduced, where we can kind of just build both robots either concurrently or one right after the other, saves time. And then the two robots are the same, right? Like they're much more similar. So in terms of performing exactly the same way, acting exactly the same way, the two robots are a lot more similar. And then in addition to that, because you've done a better job planning out your electrical, the practice bot's a lot more reliable, so you have a lot more uptime, right? I think for teams that are used to building practice robots, that robot's usually pretty crappy and tends to go down on you a lot. And so, having a better practice robot gets you more practice time, just straight up. And so that's a big benefit here. One of the things that I kind of don't address directly in this presentation, but I want to mention here, all of this still requires that you actually know how to route your wires properly, right? So nothing about this workflow makes you better at wiring a robot. It just gives you the tools to plan it out, right? And so you still have to, know the right ways to constrain cables and how to build in enough slack that your arm is not going to pull on the cable when it goes to full extension or whatever. So you're gonna, if you can do all of that together, you'll see some of these benefits. Finally, just your final model is just better. It's just more complete, more polished from the beginning. Some of that benefit is in terms of communication, documentation, just saving yourself time. I am sure that there are other people other than me that have fully assembled a robot without an RSL. I'm sure I'm not the only one to forget that, right? All right, so this screenshot you have here, that RSL block model was in the CAD before a single part for the first robot got cut. And so we didn't forget the RSL. It was in there from the beginning. It was beautiful. It was I cannot tell you how wonderful that was. And then in addition, because you're kind of like staring at your electrical system the entire time you're doing CAD, you're thinking about things that you normally forget about, like how am I going to get to this device, right? Like how am I going to install these wires, like assembly order and things like that. As long as you're thinking about it, you have the tools and you have the visualization to see that stuff and work with it. Again, it's like you have to be making good decisions, but you have the tools to enable you to make those decisions and make them very, very early in the design process. Okay, so we're going to go into a little more detail about what we actually did and how we did it. So high-level overview of the workflow. We're going to go into more detail on each of these elements in subsequent slides. So first off, we're kind of working on block CAD. We've got, the model is progressing. Maybe not all the components of the robot are in there finally or fully like fleshed out, but we've got some of the mechanical structure in place. We start adding the electrical devices in block CAD. There's a feature script that does that I'll talk about. Then once we've got all the devices kind of positioned where we think we want them to go, we start connecting them all together with the wiring runs in block CAD. There's another feature script that does that. And then once we've kind of got all that finished, we finish the block CAD like we normally would. We derive them into all the subsystem part studios, start working on detail CAD, kind of in the normal workflow that we would use. And then the one final thing that we did that is, we chose to do it. We'll talk about this a little bit more when I talk about kind of next steps. And there's some drawbacks to this, but this is what we chose to do for 24-25, is we didn't actually put the real detailed models of the electrical devices in the final robot assembly. We just used the block CAD kind of like blobs of cables and devices. That saves a lot of time, especially since the block CAD is so detailed that those are essentially like fully dependable models that that's why we did it. And it worked pretty well, but it did have some drawbacks, which we'll talk about. Okay, so going into a little bit more detail with some images of those different steps. These are some screenshots of kind of like the step where we were adding the electrical devices to the block CAD. You can see simplified models here of like the RoboRio and the radio and things like that. They've got mate connectors where all the electrical connections are, and we'll use those mate connectors later. All the mate connectors are like nicely named in the feature tree, so you know which mate connector goes to which without like fumbling around in the model either if you don't want to. Once those are all positioned, we're adding these block wires. They're just dumb cylinders, kind of swept along the path of the wire, and they're generally a little bit larger than the real wires are, just to kind of like claim that space. We'll go into more detail about how this feature script works in a couple slides. The key thing here that we're doing is you'll kind of notice all the different colors. We were kind of building a single body part for an entire electrical subsystem. So like in this image, like the battery is one, and then this like giant pink thing, that's the power distribution subsystem. There's the light green is like the RoboRio and the RSL for like communications. If we had had other sensors and stuff in here, that would have showed up in that pathway as well. The orange is the like network, like Ethernet stuff. And then there's a dark green in here for the CAN loop as well. So those are all, each one of those is a single part. All the geometry is Boolean together to like make a big single body, and then they're color coded to kind of be able to tell them apart. And then this is what it looks like in a part studio. So normally when we do our block CAD derives, we kind of set them to this like transparent purple color just to make it really clear to the designer, like this is not a real part, this is a representation part. It's kind of like acting like it would look, it's kind of like looking like it would if you were doing in context, but it's not in context. It's just make it transparent so it's not in your way. And then we do a bunch of showing and hiding to like get them out of our way if we don't need them there. And then we chose not to do that with the electrical subsystems, again, because they were like pretty high detail. We kind of treated them a little bit differently. We kept them as their like color-coded color to keep them in there. But that was mostly just because looking at the wires when they're transparent just is not very easy to look at. And then, like I said, we were inserting the actual block CAD models of the electrical subsystems into the assembly instead of like going and making a more detailed model of it. And so this is like the drivetrain subsystem and then the and then the full robot assembly. Now this is our first time through the process. There's some parts of the electrical system that are still missing in this design, so like it's not 100% complete. The full CAD of the robot is available. One of our team members posted it on Chief Delphi like last night, so it's available if you want to go look at it. You'll see there's plenty of stuff that's not there, but we got a large portion of it, and we got the most space-constrained things designed from the beginning. Okay, so let's talk about the actual tools that we built. So there were two big ones. The first one is this Block CAD insert feature script. This is not an entirely unique concept. There are one or two other feature scripts out there that do a similar thing. And it's basically, we built this library of these like simplified single body block models of common electromechanical devices, right? We only made the devices that we use on 3005, but like you could make anything that you want, any of the motors, any of the sensors that are available on the market. But we basically made this library just in the same document as the feature script. And a lot of these are optimized for the electrical kind of use case, where we've got the mate connectors, obviously, for the wiring connections. What we did was we designed block versions of the connectors, like pre-plugged into the ports with no wire or cable coming out of it. And that's kind of like to kind of represent the positioning of the wire and the accurate space claim of, yeah, this plug is in this port. And then we just kind of like pre-populate all the ports. Don't worry about it if you don't use all of them. They're just kind of there. It's fine. We've got a lot of configurations, especially for things like this motor and gearbox model here, where like it's a max planetary. You can change the number of stages, and you can change which motor is on the front, and it'll update kind of just based on all of your configuration options. Basically, we started off using the built-in derive feature to just bring these block models in, but because of the way that the derive feature script works with context merging and stuff, it doesn't actually work for this, because you can't context merge multiple models of the same configuration in the same part studio. So when you're trying to insert, like, oh, I have 8 motors that are all the same, the derived feature script won't let you do that. So we had to kind of like, this feature script was originally a way to kind of work around that, but it ends up bundling a lot of really convenient features into all one interface anyways, and so it ends up being a lot faster, and so it's a really nice workflow. It's handling, selecting which block you want to insert, setting the configuration of that block, and then positioning it in the model. We're kind of like snapping it to a mate connector, and you can reorient it and everything, and it's a really, really simple but really powerful set of options that you have in a single feature. And then there's a few like kind of weird cases when you're bringing in like multiple different models with lots of mate connectors and things, and so this does some like cleanup work on the backside to like not have a bunch of excess mate connectors that you're not expecting. Here's some examples of like this in use, like some of the user interface, inserting a 90-degree ultraplanetary here, and like early in our block CAD model of our robot. These block models are very useful for just mechanical design, in addition to the electrical workflow as well, because you're space claiming the motors. They're just detailed enough to be very recognizable and have an accurate space claim, where like if you're just looking at the model, you know what motor or what gearbox that is just by its shape. But other than that, there not a lot of detail. Okay, and then the second custom feature we made was this block CAD wiring feature script. The idea here is, yes, we wire robots after we've built them, because we didn't have the CAD tools to like plan the wiring out in CAD ahead of time. But that's not the only reason we do it. We actually do it because the methodology of figuring out the wiring on the real robot is really intuitive and really good for iteration, especially for a material that's as complicated in its behavior as a flexible piece of cable, right? That's not such an easy thing to like, how is this cable gonna bend, and like what bend radius can I use, and how is it gonna move when this arm? It's a whole lot easier to figure out in real life than it is in kind of a rigid CAD model. And so the idea of this feature script is like, let's try to emulate as much of that workflow and that kind of intuition into this feature as we could. And we did a decent job. It's not perfect, and we'll talk about that a little bit in the improvements of kind of like some things we've done since then to make this a little bit better. But the idea is like you start off knowing I'm connecting from here and I'm connecting to here, right? You've got the start and the end point. You pick those first. You know what those are. Those are easy. You're just picking mate connectors on two of your inserted blocks in like the vast majority of cases. Generally speaking, you don't know how long the cable is going to be. Sometimes if you've got a pre-made cable, you do know that length ahead of time. We'll talk about that in a little bit. But generally speaking, you don't really care how long this run of 12 gauge wire is. You just need it to get from point A to point B and generally be, you know, properly constrained and not get in the way of anything. The behavior of, you know, the cables in terms of how they bend and loop and things like that, we wanted that to be handled in a kind of organic, like realistic way. And so like when you're kind of like going from your belly pan up to another piece of structure and you're doing these like kind of S bends, or you're doing a loop to take up, you know, slack in some part of the robot, we wanted that to kind of be pretty easy to replicate in this feature without having to create like a whole big like helix to do a sweep and like do a bunch of complicated CAD work. And then what we wanted to be able to do was like build up the whole like between point A and point B, like where does the cable go? Be able to kind of like build that out, test it, see what it looks like, tear it all apart and try something else, you know, like a really simple and straightforward workflow, or make radical adjustments to that path in between, you know, in a very like tight iteration loop. This is all about time, right? It's all about going fast. And so, you know, anything that's not, any detail that's not helping you actually solve the problems that need to happen on your robot, we weren't putting into this feature. So like multi-conductor cables, like we use a lot of peel apart, like 12 gauge cables, got the black and the red like together. A lot of teams use that. Like don't represent that as two wires side by side, just represent it as one large round like body that's tracing the path, right? That keeps your regen time good, like it's claiming the correct space and it's good enough for what you're trying to do. No connectors, right? Like the connectors that are typically part of your like the cable and harness workflows, they're not handled here. It's purely just the round body of the cable. The connectors are handled by the block models, like I mentioned. And then try to minimize the number of extra features that you need in your feature tree to constrain and route the wiring the way that you want, right? There's a few options in the feature script. You can route through mate connectors. That's definitely the bread and butter. You can connect through points and like you know, vertices, and then you can also use a sketch to drive the routing as well. There's a screenshot on another slide that I'll show you. And then you kind of are defining this by, you have a list, just an array of intermediate stations for the wire, and the intermediate stations can route through all of these things that I've mentioned, and you can kind of like change parameters for each one. You can reorder them, you can add them, insert them, delete them, and kind of just play with like where are all the stops that this wire goes through to get to point to get to the end point. Here's some screenshots here. You know, this image on the right is like one of the more complicated cable runs on the robot to get from the power distribution board to the like one of the swerve modules. Had to route around a bunch of stuff. You can see, I don't know how easy that like feature dialog is to read, but there's a list of intermediate stations there of like with all the different options. And then this image on the right is the sketch that we used to do the majority of our routing on the belly pan. One of the nice things about this is, one, it's just one sketch that routes like a whole bunch of these different wire features. And then the other thing too is this sketch is just placed on the like belly pan of the robot, and then the feature script handles like offsetting the wire, so it's like sitting on the belly pan realistically. We also did some like stacking where we'd have multi-level cables. That's all handled through the feature script, so you don't have to be like inserting planes and offsetting them and then putting sketches on those planes to create like a center line sweep like you would do if you were using the sweep tool. Okay, so that's kind of like that's as much detail as I want to go into on the tools. A few issues we encountered. We just didn't make our 12 gauge wires big enough. Like we used, I think, 8 millimeters. Like they just should have been larger. So we still had some places where like, ooh, we don't have quite enough room to route this giant bundle of cables through. That was largely a function of how complicated the robot was. The other thing too is like we're using a lot of spline paths, and The way the splines are defined, you're kind of, one of the key things that you're spending a lot of time in the feature doing is you're adjusting the derivative of the spline, which is kind of like the curvature at the two endpoints. And that doesn't produce a very realistic or natural shape for the wire. And the other thing too is it's very dependent on where that spline is going, of like whether it produces the shape that you want. So the feature kind of pops up all these like little manipulators is what they're called, like little arrows. You just drag them to kind of adjust the shape of the wire. But you spent a lot of time fiddling with those to get them to work. And then if I would go and like, oh, I'm gonna move the RoboRio 2 inches to the left, the feature would sometimes break because the spline would be like self-intersecting or whatever. And so it was just a very labor-intensive part that was not in what we were trying to achieve. And so like there's some work that's been done on that to fix that problem since then. The other thing too is like when on these really long cable runs, we would want to like, you know, define connections at the you know, PDH, and then define all the connections on the motors, but then we would end up with these big bundles where it's like, okay, here's a whole bunch of cables running through this area, but sometimes we would want to like, yeah, I want this one to go from here and actually connect to this other one over here. Like I wanted this to go from the top of the bundle to the bottom of the bundle to make like splitting it off. And you would have to redefine all the intermediate stations, which can still be kind of time consuming for really complicated cable runs. So that was a little bit tough. Because we were using the block model for the electronics, we didn't have a weight for the entire electrical system. When you're building a 3-stage elevator with 1 million motors on it, that's like 15 plus pounds of wire, right? Not including the devices. It was like a lot. So we ended up in a much worse weight situation than we expected because we didn't have a good weight estimation. So that was something that was a little bit unfortunate. And then the other thing that I mentioned was these set of features don't really handle preset lengths of cables either, right? Like if you've got a pre-made cable with plugs on either end, you know, this is kind of just gonna make the wire whatever length it is based on the intermediate stations. You're kind of like entirely left to your own devices to like bundle up the excess. We'll talk about some kind of approaches to these here soon. These are kind of some of the next steps that I see and some work that I intend to do or work that's already been done to kind of improve these. Like I said, this kind of presentation, slide deck is largely intended as like, it's partially intended as documentation of this process as much as it is like a, I want to share this with you thing. So I'll kind of just gloss over these, but if you want to go look in more detail, you can. A lot of these problems that I mentioned can be fixed with kind of like just a process or like workflow improvement rather than changes to the features themselves. It was more just like, it's still a pretty complicated thing to tackle, and so there's a little bit of a learning curve of like, what's the best way to implement this on a robot? You know, we need to tune our cable diameters better. There are some things we can do to like, instead of doing these really long, complicated runs all in one feature, like define a like break point in the middle of like, here's where the bundle starts, bring all the wires up to here, then do a separate set of features off to the end. There were some reasons that we didn't do that to begin with because the feature calculates the total length of the wire, which is really useful for us being like, how much wire do we need to do this, right? And so like, but there's some improvements that I have planned to like kind of help make that a little bit more workable. The CAN loop especially was a little bit weird because all of the like motors are part of the subsystem blocks. So like we have like an elevator block and all the motors for the elevator are just part of that blob. You know, the swerve modules have their own motors. And so the CAN connection is going to each one of those. So like the method that we did of creating a solid model of each electrical subsystem doesn't really work for CAN because that solid model is the entire robot, right? And so we did these little jumper things in the CAD just to physically connect the bodies together. I didn't want to use composite parts because when you're having a student go start a model, by default, Onshape filters out composite parts, and so they open it up and they're like, block CAD, right? They see a list and they just select stuff from the list. Well, the composite parts aren't there and they don't select them, and so they just don't put the wires in the model, which defeats the whole purpose. And so I was like, I really don't want to use composite parts for this because they just will get forgotten. And so I think looking in hindsight, I think I probably should have just like pushed us to use composite parts and then just done some training on the part of the students to just make sure they don't forget it. There's also not that many subsystems on a robot, so for me at the end of a meeting to go through and like check each one individually and just make sure they inserted it properly is not that much work. And I think a very short amount of training would have solved that problem. Mass and weight, again, I think it's a workflow thing. I think we should fake the density of the cables, right? Because the volume is still a relatively accurate thing, so just like estimate a linear volume for the cable diameters you're using and just put that in. That'll get you close enough. And then I think a configuration to not have the detailed model or not have the blocks of the devices and only have the cables would be useful. And then when we go to put it in the assembly, we put the detailed models of all the devices, then we insert the block of the wires only in that configuration, and then we do that. That's a very in the weeds thing that, like, I don't know if you care about or not. We need more blocks in the feature script. It's super custom to 3005, so like it's not going to be useful to very many teams who don't use the exact subset of motors and devices that we do. Want to add a feature to be able to just like grab external part studios if there's a block that doesn't exist already, because that's obviously going to be a problem. Tweaks to the mate connector like coordinate system that I didn't love the way that it is right now. The main thing to the wiring feature script is just making the kind of like spline behavior better. This has already actually been done. I've got some screenshots of like a before and after. This is kind of a hacky like fix, but I did a decent amount of stress testing and it seems to be good enough that it's like produces a much more realistic wire. It's not perfect, but it's significantly better than it was. And generally speaking, when you're putting this in, you don't have to fiddle with those derivatives very much at all to get this to like work. And then you can move devices around and it doesn't break. And there's a few other things there. So if anybody's interested in this, this project's in a little bit earlier of a state than I would normally like want to share something like this, but because I've moved and I'm not going to be on the same team anymore, it was kind of like, all right, well now's the time to share it. It's also complicated enough that I'd like to see how good this is for not specifically me and my team and the way that we do things, because like it's kind of hard to tell, like is this just an us thing or is this actually useful to other people? And so if you're interested in this, you think this would help your team kind of, do better electrical design on your robots. I have links here to the robot from 3005 from last year that you can kind of look as an example. I've got links to the 2 feature scripts. If you feel like using them, this slide deck will be shared and then you'll be able to access the links. I think these are all being posted on Chief. If not, I'll make sure it is. And then, use them, give me feedback. Design your own insertable, like simplified blocks. If you have really good ones that are common, I can work on adding them to the feature. So I've got some work to do on the feature scripts to make them a little bit better, which I intend to do, over the next, month or two. I may make breaking changes, so like using these on like off-season projects is probably good for now because they may change drastically before kickoff. All right, questions? Yes.
I assume with Block CAD you're using a single part studio?
Yeah.
Because I've tried wiring and assemblies and it just doesn't seem to go anywhere.
Yeah. Doing it in a part studio is a much better workflow. Okay. I keep going back and forth on what the right approach was. Talking about rebuild times, like this wiring feature script does take a while to rebuild. With using composite parts and kind of like those process improvements, it might make sense to just make a separate wiring part studio and do either in context or derive in the Block CAD, just so they're like in separate studios. But I keep going back and forth in my head on that. There was a question over here.
Yeah, do you know if, I know you're just assuming 12 gauge wire, do you know if that accurately models the cable, like minimum cable bend radiuses?
No, that's kind of up to you.
Okay.
Now, the truth of the matter is we just abuse the hell out of the wires. Like they're just like, it's gonna bend as tight as I say it's gonna bend, like to a certain point. So like, that didn't really seem to be an issue. Originally I was like, oh, I'm gonna like try to like constrain the curvature of the spline and stuff. That gets really complicated. It was beyond my ability to write the code for that. And I also was like, that's really just not the way that you would wire it in person. So it's just a very visual kind of like gut feel process.
Yeah.
So.
Did you only include 12 gauge?
No, that's obviously the largest like volume connector, but like we did the battery cables for the power connections, we did the CAN loops, we did the little tiny like wire for the RSL. So it was like, yeah, the feature script literally just has a box that you just type in a dimension of what the diameter is and you just pick it. I was thinking about maybe adding a drop down to like have built-in presets, but I got the diameter that I was guessing wrong when I did it the first time, and we just used that for the whole season, and so I don't want to commit to like presets that are incorrect. So, any other questions? Yeah.
Did you find that the reported wire lengths were accurate enough to pre-cut wires?
Ish. So like, we're not really handling the like crimping of like Anderson connectors and stuff. So like, there's a little bit on the end, but like if you cut it 4 to 6 inches longer than what CAD said, yeah, it's probably going to be pretty close. There were several places where you used the length, and then there were plenty of other places where we didn't. Yeah.
So the 3005 robot this year had like a really impressive like extender for your coral mechanism. Which
Yeah.
Obviously, a bunch of wires had to run through that. Did you even touch any of that, like trying to model any wires for that, or was that just like you still had to feel it out?
So we started on it. When you go look at the CAD, it's not there. The cable management on the coral ejector was done, and the like cable carrier for the extension is there. That was kind of just a ran out of time, did things in the wrong order kind of a thing. And you know that we've been through this a year, I think we would definitely make sure those were included the next time. So yeah.
So when you're doing something like that with like an elevator, then if you set your mate points, is the feature script smart enough to know if, like to model like an elevator fully extended for lengths, or would you have to set up the connection with the elevator fully extended and then
Yes.
deal with the loops once it's in person, I guess?
Yeah, so that's kind of a limitation of the block CAD kind of process of like, yeah, the elevator doesn't really move. We do a block CAD assembly that's part of this, but that's kind of more of a, that fills the role of like what they were talking about in the last presentation about like, I want to line this up to a field element and like change the position. We don't do that with the final robot assembly. We only do that with the block CAD. And so like those two things that's not really related to the wiring thing. What we did for the elevator was we had the cable carrier modeled as a block in its retracted state, and then we would just route all the cables to the top, and then we just route a separate set from the exit, so they were split parts. And then those ended up being separate bodies too. So it is, we got like, I think we're ending at 5:30, is that right? Okay, we got 4 minutes. We got some time for some more questions. Anything else? Yeah.
Since you've moved teams, is this a project you personally plan on continuing wherever you land next, or is this just now open for like all teams to join?
Yeah, I plan to continue working on it. It definitely had a lot of benefits. I don't know what team I'm going to be on up here yet, right? I'm still kind of settling in. So it depends on what team I end up with, if that's something they're interested in, like what their existing workflows are. You know, there is quite a bit of like overhead to this. Like it is much more CAD work, right? You have to be very disciplined in your model, right? If you're just starting out with a CAD team, or you're very early in your design, or have a lot of inexperienced designers, like this may be more trouble than it's worth. It's also obviously more beneficial if you're building much more complicated robots than if you're building like if you're building like an everybot or a kitbot. There's enough empty volume on the robot, you'll be able to figure out the wiring and not have issues. So yeah, it's kind of TBD. Anybody else? Yeah.
How when you guys actually went to build the robot, how well did it translate?
Very well. So that kind of, I showed the back area of the robot. We had to make some tweaks in the real version to make that work because we installed like Anderson pigtails on our motors, and we didn't want to like make those a different length for every motor uniquely, but we wanted the Anderson to be like in an accessible location. So that required some adjustment when we were assembling the robot, but we had already put enough like cable carrying and supporting components in the right places that it didn't require us to adjust any mechanical stuff. It was just, okay, well, I'm gonna actually route this over here or fold it back on itself a little bit and add a little bit of cable length so the connector's in an accessible spot. One of the improvements that I had thought of for the wiring feature script that I may do if I have time will be to add an option to like displace a mate connector down a certain length of the spline path. So like you can just say, there's a mate connector here, that's where the connector will be if it's 12 inches off your motor. and then that will help you. You can either model the connector there if you want to, or you can just visually see where it is and make adjustments to get it in the spot you want. So that shouldn't be that hard, and I think that would be useful. Anybody else? All right, cool. I think last session of the day, so that's all I've got. Thank you guys very much.
We are good for today and until 7, which is when we're going to Bolero. So if you're signed up for that, great. If not, there is a link on the conference webpage to just add that to your registration.
It was a lot of fun. It was a lot of fun. It was a project for sure. It was a lot of fun. Well, then how are you going to AI code the whole thing?
Yeah, because all we do is okay, the wires are going to go like that. Just like you said, we hand wave it. We've had the experience of, oh, that's one of those wires that didn't even close. We've gone through all this stuff.
Yeah, it was a very common like it's like, we were building very competitive, very successful robots, and still just like,
No matter how good you are, you always get to that point of wiring, and you're like,
it's, yeah.
all right, it works.
We tried.
You think about it in
You try to
advance.
put the electrical components in,
Yeah.
and then at the end, it's always like,
Inevitably, there's one wire.
inevitably, there's
Should go through that frame.